oxide is the oxygen vacancy. The reason I already explained. Because oxygen, you supply the gas into the chamber, MU3 or LV chamber, oxygen molecule, two atoms of the oxygen very strongly bound together, and it's very difficult to break this bond and let the oxygen atom react with zinc. So you always have the very high density of the vacancy. That's make the materials you prepared is an conductor. So the Fermi energy located in the conductor band, for you need to make the intrinsic zinc oxide semiconductor, you need something to reduce the density of the vacancy. I think Professor Feng also did a lot of this kind of thing. Many people working on the mechanism of this vacancy or the defect origin in the zinc oxide, but still not the mass development. So this is very similar. I just want to mention another case, gallium nitride. If you look at the study before the 1994, so a lot of people try to decrease the density, the defect density of the gallium nitride, because as prepared gallium nitride is always an N-type conductor. So that's make the P-type doping extremely difficult. So because you have the very high N-type background carrier density, to make the P-type doping, you have to concentrate all the N-type carrier, and then you get the P-type doping. So in the 1994, Dr. Nakamura in the Nichia, this company, they find a method. Of course, there are some other story. I just in short, he find a method to cure this, to get this efficient P-type doping, and then they make the blue diode-based gallium nitride. I think that's the big advance in the gallium nitride, the 3-5 semiconductor industry. So now you see this laser pointer. Although there are not so many companies produce the blue light laser use gallium nitride, but that's available in several companies like Nichia in Japan. And so basically, for this semiconductor topological insulator, we have this problem with this intrinsic defect. Either the N-type in the case of the bismuth telluride or the bismuth selenide. Antimony telluride, you always have the P-type doping because the anti-side defect, most likely the same thing. So for semiconductor industry, the first thing you get all the thing down is this starting materials. You talk about semiconductor for the bipolar doping. Your starting material must be the intrinsic insulator. That's the best. Gallium arsenide, silicon. If you get the intrinsic insulating material or semi-insulating material, that's easy to do this bipolar doping. You either can achieve N-type doping, you also can easy to get this achieve this P-type doping. NP make this diode. Okay, so this is the thing. So for the bismuth selenide, so on, we need the shift the Fermi energy down to the gap. So I just mentioned the group. I just mentioned a living group in the material group. The problem, I think, this self flux method is not the best method to prepare the intrinsic topological insulator like zinc oxide. Some people working to find the best method or way to prepare intrinsic zinc oxide. Same thing here. So my group had developed starting around 10 years ago. We developed some of the combination system, combining the MBE, high vacuum MBE, and STM and ARPES. MBE is a well-established technique. With MBE for the semiconductor, you can easily achieve this layer by layer growth. Means you can control the material growth at atomic level. STM, everybody is a very good eye to see individual atom, to look at the morphology in the atomic scale. You also can see the local density electronic states related in the real space. So that's another very powerful technique. And ARPES, of course, in the momentum space, you see the better structure materials. So by a combination of these three systems, basically you can control the growth in the atomic scale. You can study the material, layer by layer, and understand the evolution of the electronic structure or morphology at, layer by layer at atomic scale. So this is very powerful. So this is one of the picture of our system, made by the German company Omicron. So MB here and FTM. Of course, the ARPES spectrometer comes from this center in Sweden. And now we have the both system MB combined FTM and ARPES. So once we start the growth, we have to think for the MB growth. If you have some experience, you have to understand the vapor pressure. So if you look at this, I just showed the vapor pressure and the function of the what's the temperature for the different element. So this is the vapor pressure of selenium. Even below 100 degrees C, you already see the evaporation of the selenium. Of course, just like oxygen, even in the ambient room temperature, with the vapor pressure already to the 1 atmosphere. So it means, you see, the selenium is very volatile, with increasing the temperature, that's the vapor pressure becomes very quickly, very high. This is the case of bismuth, just like the standard metal, and they have a low pressure. I think, let me see the arsenic. This is the arsenic. Arsenic, I think this is something, the gallium. Gallium around here, this is the gallium, this is arsenic. So if you look at the vapor pressure change and versus the temperature, selenium is very similar to the arsenic for 3,5 arsenic, and bismuth for this gallium. Gallium have a lower the vapor pressure. So for making the gallium arsenide using the arsenic molecule and the gallium atom in the MB chamber, we use these 3 very famous standard 3 temperature criteria. Since the similarity between the selenium and arsenic, bismuth, and gallium, probably you can use the same 3 temperature criteria for the MBE growth of high quality selenium bismuth selenide and that for 3,5 gallium arsenide. So by looking at this vapor pressure similarity, we immediately get an idea how to prepare high quality, the stoichiometry or metric bismuth selenide in the composition of 2 to 3. So this is very important. I think this lecture particularly made for the students. If you start the MBE growth of the one compound, you have to really understand the property of the vapor, vapor pressure behavior for different elements. So I just show you with this kind of vapor pressure, what kind of kinetics you can imagine in the process of MBE growth of this compound. So you have the substrate, and you have some of the KCl here, and the KCl here, and you put your raw material into the KCl, you heat your KCl, then in the case of the bismuth or selenide, bismuth is evaporated in the form of a bismuth atom, but the selenium come as this molecule. And in other words, you have the selenium 2 and the selenium 3 or selenium 4, sometimes selenium 6. They come out from the cell. So on the surface, the reaction will be take place by the breaking of the selenium molecule into atom, then mobile on the surface with the mobile selenium atom react with the mobile the bismuth on the surface, then they react they become this is the compound. So this is the normal just like gallium arsenide. So then we use the standard MBE growth for the gallium arsenide to grow this bismuth selenide. So sooner we can this is the reader pattern reflecting high energy electron diffraction pattern during growth of the bismuth selenide. You can see this is 0, 0, 0 diffraction, 0, 1, this is 0, -1. Along all these diffraction you have this very long bright line. This if you know the principle of this diffraction, and then the very long straight line indicate the morphology of the film is very flat. So then we measure the intensity and the intensity change and the function of growth time as I put here is the intensity of individual diffraction spots and the function of growth time. You can see the intensity oscillation. So the one cycle of oscillation indicates that the deposition of one atomic layer. In this case, one unit cell. So we can really get this layer by layer growth. So as schematic shown here. So one cycle oscillation, represents the deposition of one unit cell or one layer. So I just mentioned that the growth kinetics of the bismuth selenide is very similar to that for the gallium arsenide because of this similarity between the similarity in the vapor pressure. So to demonstrate that, I asked my student to do the three experiments. So by looking at this intensity oscillation, you can really determine precisely the growth rate. So we studied the growth rate and the function of flux ratio of bismuth and tellurium. So in this figure indicated that I think we use we fix the bismuth flux and the tellurium flux. So we change the substrate temperature from the 540, 543 to the 563 with the fix of the flux ratio and only change the substrate temperature. You can see we get all cases we get the oscillation. The separation between the oscillation is the same. Means the growth rate is independent of the substrate temperature. This is the one experiment. The second experiment is we fix the flux of bismuth, also the substrate temperature, only change the flux of the tellurium from the 523 Kelvin to the 543. So in this case, the vapor pressure, the vapor pressure changes dramatically because you change the temperature, and I mentioned in the vapor pressure versus the temperature, so the tellurium, the flux will be changed dramatically. But in this case, you see the separation between the separation between this peak in all the three cases are same. So this indicates the growth rate is independent of the tellurium flux. This is extremely important if we want to do the MBE growth. So this is the second experiment. And the third experiment, we fix the tellurium flux at this temperature and also the substrate temperature at this temperature. We only change the flux of bismuth from this temperature to this temperature. So in this case, you can see the separation between these two peaks change. The higher the bismuth flux ratio is, and the shorter the distance between the peaks means the growth rate is linearly dependent on the bismuth flux. So by this three set of experiments, we establish the growth dynamic of MBE growth dynamic of bismuth telluride and bismuth selenide. So the students, if you want to really do the MBE growth of the topological insulator, just study this paper, just do the same experiment. Or if you get another kind of compound, you want to do the MBE growth, you look at, understand the vapor pressure versus temperature, and you decided that you prepare this kind of experiment. I think you will understand the growth dynamic, then you will control the growth of MBE, then you can get a very high quality film. So basically this is the comparison between the gallium arsenide, the growth condition for gallium arsenide bismuth selenide. So gallium arsenide made by the arsenic and the gallium, arsenic is the molecular, and gallium is molecular in the form of molecular, gallium in the form of atom. So bismuth selenide made by the bismuth and the selenium. Selenium is evaporated in the form of molecular, but the bismuth is evaporated in the form of atom. So if you use, in the case of gallium arsenide, we use a very high arsenic rich condition. Typically, in the standard MBE groups of gallium arsenide, this flux ratio is around 50. The reason is with this kind of a very high very arsenic rich group condition, we still get the very high quality gallium arsenide. The reason is this 3 temperature criteria. So the substrate temperature is higher than the mass higher than the temperature of the arsenic source, but it's much lower than the source of gallium. So with this one, even you have much more arsenic supply to the substrate, since the reaction rate is only limited by the flux of the gallium or available of the number of the gallium, so the extra arsenic will be immediately evaporated out of the surface, since the vapor pressure, the substrate temperature is much higher than the arsenic in the evaporation temperature, so that the extra arsenic will be gone. So only left, if you have one gallium, thermodynamically stable with the one atom to form the gallium arsenide. So the extra arsenic, because this substrate temperature is much higher than the evaporation temperature of arsenic, so the extra arsenic will be gone. So you only have the 1-to-1. So same thing happened to this bismuth selenide. So these 3 temperature criteria for this MBE groups of the 2 elements with big difference in vapor pressure is essential. So I actually spent quite a long time to explain this one, because this is very, very important to get the high quality materials. Oh, I talk. So this I just showed the result. So after MBE groups, we took the sample to the FTM chamber. You can see the morphology, half micron by half micron. You have 1 atomic step, 2, and 3, and 4. And if you look at the atomic flat, the terraces, you see this kind of high energy resolution FTM. You see the surface helium atom. Most importantly, in this case, you have a very small density of defect. Okay. And then you measure the band structure, just move to the in situ aperture chamber. You see the beautiful direct count. More importantly, near the Fermi energy, you have no this conducting band. Okay, conducting band is located probably around this place, and also by the change the growth temperature or the flux ratio, we can control this kind of the electronic structure very nicely. So this is an N-type conductor. Now it become the intrinsic, and now it even become the P-type. So this is very easy manipulate electronic structure by this MBE. So for one cycle of the sample growth, we only need 1 or 1.5 days if the experiment going well. So this is can save the time compared to the cell flux ratio. You need several days for one cycle of experiment. I just show the bismuth selenide, and you get atomic flat morphology. If you zoom in, you see very few defects, and if you measure the band structure, you see the Fermi energy located, the gap only cross the Dirac-Kaplan, and then we even extend this kind of growth MBE group constitution to the ion selenide. So ion selenide is a ion-based the new superconductor. Basically, this compound made by the 2 elements with the similar vapor pressure property as the bismuth selenide. Because ion is also a low vapor pressure materials. Okay, this is the high vapor pressure materials. And then on the graphene terminated silicon carbide, we prepare 1 unit cell ion selenide. if you zoom in, you see there is very few defects after deposition the second unit cell, and also defect density very low, and for 4, 3, and 4, and so on. So basically, you can grow the layer, the material layer by layer. The most important, the density of the defect is much lower compared to the single crystal of this ion-based superconductor. Any of the so this kind of quality sample cannot achieved by this single crystal growth method used for the ion-based superconductor in the most cases. And we even prepare very homogeneous film for the potassium doped ion selenide, and you can see the morphology is very uniform. You measure different the local density of the states at the different locations, so the gap is very uniform. So far, I think I talk about the most important part of our thing. So I just want to give the emphasis to the students. So once if you are an experimentalist, if you want to do the good transport or other study, optical studies, I think you start with the best sample. If you have your lab have some of the set up to grow the material by yourself, that's great. So I think I just want to emphasize the importance of the materials to the students. If you look, particularly I use this example, like the cuprate high temperature superconductivity discovered by Dr. Bendenos and Muller in 1986. So this is a big discovery, but discovery is the materials discovery. Since so far, we have almost no idea about the mechanism of how the high temperature superconductivity works. So even the understanding is the massive. I shouldn't say, but maybe even poorer than the before the discovery. Okay, particularly after the discovery of this ion-based superconductivity, and I think the mechanism become more and more difficult to understand. But this discovery, the field become become very hot because of the materials, not the physics. This is the graphene. If you look at the citation for the Nobel Prize, here for groundbreaking of experiment regarding the two-dimensional material graphene. Of course, the important thing is second year we discover this half integral quantum Hall effect. But basically, material is very important. So, of course, I just emphasize this point. So with these things, we are very successful in the MBE group of this intrinsic topological insulator. We did a lot of experiment by the in situ FeSe. We demonstrated the surface states is protected by the time universal symmetry predicted by theory. We also use the FTM low temperature demonstrate the system is a massively direct fermion system by observation of Landau quantization and other things. So this is some of the quantum interference pattern observed on the bismuth selenide surface. So I will not talk anything about this. Also the absence of back scattering by this analysis of this quantum interference pattern. This is the first observation of the Landau quantization in the case of bismuth selenide by FTM. Also another group is the Japan group, the Hanaguri. So I just also now we at the beginning we have a difficulty in prepare the high quality antimony telluride, but now we can get a good material. So we see the very beautiful Landau quantization. So now I talk the topological part. I mentioned the importance for materials, and this is the most important part of my talk or our experiment. So the MB, we can get a very good materials. With that good materials, we see some of the fundamental. We observe implemented some fundamental property predicted by theory. I think so far there are not so many transport experiments demonstrated the novel, exotic physical property of topological insulator. So this is limited the material itself. We need something something else. For example, as the theoretically predicted, the first important thing is the quantum anomalous marijuana fermion. That's again is a very hot topic going in the field now, and also magnetic monopole proposed by Shouxing and many things. So, but unfortunately, in this very emerging field of topological insulator, very few transport experiments demonstrate this. A lot of the property I think discussed in the workshop in this summer support. So we are probably the first group to see some of the really very, very exciting transport experiment. That's quantum anomalous Hall effect. So in the last part, I just quickly go and theoretically proposed by, and in a piece, I think 1988 by the Hadan, use this inhomogeneous magnetic field applied to the graphite. And later on, and there are a lot of theoreticians working on this one, and I think Nagawata Shouxing didn't use I think Professor Liu Qian and Yun Sun Qing, the next speaker. Basically, we mainly follow the idea of magnetic doping by Shouxing. As you can see, this PRD paper, we use this topological insulator magnetic interface heterostructure. Later on, same year, they proposed the idea using the magnetic doping into this two-dimensional topological insulator mercury tailored quantum well structure. And 2 years later, they also studied the magnetic doping property in these three compounds. And later on, together with the Zhang and BizTes, they really studied this system, and I think the quantum anomalous can appear in this magnetic doped BizTes cylinder family. So I think for experiment to realize this quantum anomalous, we need a thin film, because still it's very difficult to prepare high quality insulating topological insulator. So using a thin film, we can reduce the contribution of the bulk trivial electronic states. Also, to realize the quantum anomalous, the second criteria is this ferromagnetic insulator with the perpendicular magnetic anisotropy, and basically you then open the gap at the Dirac point, then you expect the quantum anomalous effect. I think, for to prepare the 2D field, I think I already talked about the MBE goals, and in this case, you cannot be, you have to realize if you make the magnetic doping will reduce the spin orbital coupling, so you have to control the, nicely about the doping level, and the magnetic doping is the most difficult. So by this kind of gap opening, if we measure the Hall resistivity and the function magnetic field, you should expect this kind of curve for the quantum anomalous Hall effect, particularly near the zero magnetic, at the exactly zero magnetic field, you see the full quantization of the Hall resistance at this value. So this is the curve we want to observe by the magnetic doping of topological insulator. I think I really talk too slow. Let me quickly. I have 5 minutes to finish. So according to the proposal by the BizTes, Fangzhong, and Shouxing, we first try the chromium ion doping of bismuth selenide, because this guy has the largest bulk gap, about 300 million UV, and also written in this paper. Unfortunately, and even at the high doping level up to the 22% chromium, so the material exhibit this paramagnetic property. So of course we see some other thing, other interesting property of this magnetic